Welcome back. This is video 1 in section 5 of the course, the final section, the last series of videos. Today I'll be talking about material science or engineering materials, how different materials are used for various engineering applications. So let me get my slideshow fired up. So in my discussion today and in the material science class you're going to take, I'll be going over 4 main classes of materials, 4 different types, kind of broad categories. The first one, the most common for engineering applications, is metal, ceramics. I'll talk briefly about polymers, and just mention composites, which are really just a combination of some of the other classes. All of these are going to be studied in more detail, like a lot more detail, in material science, which is CHE 2501. We will be taking that next year, along with all faculties or all departments in the engineering program. So it's one of those common courses that everybody takes because it's so important for all types of engineers. So to start with, I'll talk a bit about metals. They're by far the most commonly used material for construction in chemical processing equipment, and it's based largely on the physical properties, what you can do with metals that you can't do with some of the other classes of materials. So they're essentially defined by physical properties like their ductility. So that just means the ability to shape it or form it. So, making a pipe or a sheet metal or parts for a car, like all of that is done by being able to form and work metal. While at the same time, metals are also very strong, so their ability to withstand forces is quite good. They are fairly dense, so high weight or mass per unit volume. And the main characteristic why these are so good is that they can withstand high forces, high pressures, and they can be used for a wide range of different types of equipment as a result of the ability to withstand those forces and pressures. And because you can form them, you can get whatever shape you want for your equipment. One main type of metal that I want to discuss is steel. So in the last couple hundred years, by far the most popular metal is an iron-based alloy called steel. So iron is the primary component in steel. However, there's a small addition of carbon that's in there in order to improve the properties. Iron by itself, if you just have raw iron, it's somewhat weak, so it doesn't have the structural strength that steel does. But by having tiny clusters of carbon, which end up locating themselves in between the atoms of iron, it causes those atoms to become stronger, because essentially the iron crystals can't slide over one another, so when they slide they don't have the strength, and by putting carbon in the alloy, the carbon actually locks those iron atoms in place and gives the steel its strength. There are other types of steels that exist as well, where you add different alloying elements. So steel is considered an alloy where you mix different metals together. A common example is by adding chromium to a normal steel gives stainless steel. So the chromium there provides protection against corrosion. That leads me to a discussion on corrosion, where it's essentially the primary drawback of metals is because they're really likely to corrode, and that corrosion is what we call an electrochemical reaction. And if you have a material that corrodes, it will actually lose structural strength and is no longer useful if it's susceptible to corrosion. So here what's happening is the metal atoms, the solid metal, get converted to metal ions, so they give off electrons, and that effectively will dissolve the metal. So once you have metal ions in solution, they're no longer part of the structural support of the material, and you lose strength. So here's a reaction. So you have a metal solid going to a metal cation plus an electron. So that electron is released, and the metal ion is then essentially dissolved into an aqueous solution. Here we talk about an oxidation. That's the process by which the metal loses that electron. That occurs at something called the anode. For those of you that have taken an electrical circuit course, this is essentially cathode, anode. These are where these electrical reactions are occurring. And you have a flow of electrons from the metal to the cathode. At that other location, the electron gets consumed in a reduction reaction, so the electron gets added and to form a different compound, and that reaction occurs and it sort of absorbs all the electrons that are being dissolved from the metal. So here's just a simple diagram showing an anode. Some metal is giving electrons to the cathode, where the metal ions dissolve into a solution, and you will ultimately lose the metal that you're starting with. An example of that would be car rusting. So the body of your car, most of it would be made of steel. If an aqueous solution, especially if it has salt in it, in the Maritimes it's actually really bad because of the presence of salt on our roads. That salt provides an aqueous solution that conducts really well, so the metal ends up dissolving and getting carried away in that aqueous solution to a cathode, where it forms rust and you lose the structural support in the body of the car. We can use something called a redox series that describes the tendency of metals to corrode. It looks like this. So here are several metals and the corresponding oxidation reactions where they're releasing electrons. The ones at the top are what we call noble metals. They're less reactive. So the ones at the top are less reactive. Things like gold and platinum, you think of really valuable metals, those are all sort of at the upper end of the redox series. And then towards the bottom, those are the metals that are very reactive, things like sodium, magnesium, aluminum. And the lower you are, the faster and the more the reaction is going to proceed. Now, where this becomes interesting is if two metals end up coming in contact with each other, one of them can act as the cathode, one of them can act as the anode, and you get what's called a redox couple, and you'll have electrons flowing from the anode, the reactive metal, to the cathode, which is the more noble metal. Now, if you have a material that is active and it's in a solution that is likely to lead to corrosion, you can get something called uniform or general corrosion, and that's where the corrosion occurs pretty much evenly across the surface. And here the diagram I've shown, the picture, shows general corrosion, where that is an anchor for on a pier to tie up a boat, and because of the proximity to the salt water, you can see it's corroded across the entire surface. The whole thing looks orange, and that's the rust that's forming on the surface of the metal. So that's something that you can know. You can usually predict it fairly well. A more harmful form of corrosion is what we call localized corrosion, and that's where you can get a certain spot which has more aggressive conditions than adjacent areas, and so what you can get is a really aggressive attack in one spot, which can lead to either a hole or several small holes, which could ultimately penetrate the wall of either a tank or a pipe. And here's an example of a pipe that has been completely compromised because of corrosion, a localized effect. So you can see it's not over the entire surface, but you got several small holes which would have opened up into a bigger hole, and as soon as that occurs, that pipe can no longer hold whatever was flowing in it, whether it be water or some other processed fluid. So this can actually be a very dangerous type of corrosion, because normally this happens with a sort of catastrophic failure, where general corrosion will occur over a long period of time and you can see it developing, whereas localized corrosion will occur relatively quickly, aggressively, and can lead to quick and rapid failure, which could be potentially dangerous. Now, anytime an equipment is designed, you always have to be aware of the materials and make sure that they're designed to prevent or compensate for any corrosion that's going to occur. So you got to look at the compatibility between whatever your process fluids are and the materials that you've chosen. So things you can do to reduce corrosion are using similar metals. So I mentioned if you have two different metals, one can act as a cathode, one as the anode. The closer they are on the redox series, the less corrosion you'll see, because the less driving force, there'll be a reduced driving force for the current to flow. You can use thicker metal, so just allowing more metal to be present so that even if you do lose some to corrosion, there's still enough there to provide the strength that's required. You can use something called a sacrificial anode. So here you're actually using the principle of a redox couple where you put an anode on there and it's the one that's going to corrode because it's really active, and you actually sacrifice and you say, okay, I have this metal that I don't want to corrode. I want it to act as the cathode, which means I need something more active to be sacrificing itself, to be sacrificing the electrons. So you can put a small strip of, say, like magnesium or zinc to act as a sacrificial anode, and that would actually prevent corrosion in the main piece of metal that you're working with. You can build something out of a more noble metal. Those tend to be the more precious metals like gold and platinum that are very, very expensive. So as much as possible, you probably want to avoid using those noble metals, but it is another way to reduce corrosion. And in applications where you absolutely need to limit corrosion, that is one option. Or you can use something called a protective oxide, so where you allow the corrosion to occur, and then after a certain period of time, once that oxide forms, it's usually a metal oxide that forms on the surface of the metal, that can actually act to protect against further corrosion because it provides a barrier where the electrons are not able to flow as easily across that oxide. You can use corrosion inhibitors. These are chemical additives, things to reduce corrosion. And these are just generally some ways you can mitigate or reduce corrosion, but you always have to be aware of it when designing any system that uses metals that could potentially corrode. Painting the surface is the final one, where you're actually putting a physical barrier on there to prevent any corrosion. Or using non-metals, so any of the other classes of materials, if you use those, you're less likely to see any corrosion because you're not getting that electrochemical reaction occurring. So the second class of material I want to discuss are ceramics. Now, just like metals are defined by their properties, so are ceramics. The key parameters for ceramics are that they're very hard. They have a high hardness value. They are very brittle. So hardness is actually related to the force that it takes to break it, which is different than strength, which is the force required to deform it. Whereas brittleness, ceramics are very brittle because they can break or shatter very easily, even if they're really, really hard. So you can have something that's hard, but it's also brittle, where if you drop a bowl or a glass made of ceramics, they'll break, but they can withstand quite a bit of force applied directly to it. They also have very low electrical conductivity and very low reactivity. So in applications where you have really reactive systems and metal corrosion could be a problem, you could use ceramics. An example of that would be the lining of a furnace. So if you have a really high temperature reaction occurring, the corrosion of that material could be very detrimental. And so you could actually line the entire reactor with in the furnace with a ceramic lining, and that would essentially limit the corrosion that would occur on the metal because it's essentially protected by a ceramic surface. Polymers are sort of a newer, up and coming type of material that are being used for a wide variety of applications. Poly comes from the Greek meaning many. Mer just means unit or part. So polymer is literally just many parts. And it's essentially a sequence or a repetitions of a single atomic sequence. Some of the properties of polymers: they're very lightweight, they're flexible, they're tough, and generally resistant to corrosion. They're versatile, so they can be used for a lot of different applications. Now, generally speaking, you're not going to use these for structural components, but they can be used for a wide variety of other applications. They're really easy to customize, but they don't hold up well in high temperature or reactive environments, so that's not really where you'd want to be using them. I'll give you some examples of polymers. First would be polyethylene, so things like plastic garbage bags. You get a number of ethylene units all together. So ethylene is just a carbon atom with two hydrogen atoms. So put a number of ethylene units in sequence and you get polyethylene. Polyvinyl chloride, or PVC. So that would be used for things like piping and surgical tubing. So here you have an ethylene or an ethyl unit, carbon with two hydrogens, but then there's also a carbon with one hydrogen and one chloride ion. And so a number of units of these polyvinyl chloride monomers gives a polymer PVC. Polytetrafluoroethylene, under the trade name Teflon, is useful for nonstick coatings. I'm sure you have Teflon pans at home. Here you have carbon with, instead of hydrogen atoms, you have fluorine atoms, so a carbon with two fluorine atoms off it. Those units all built up gives polytetrafluoroethylene and gives really good nonstick properties. Talking a little bit about how you can classify or evaluate different materials is using something called strength of materials, and that's something you'll learn in the material science class. The strength is a really important property because it's related to a material's ability to withstand a force. Now, in terms of engineering, a lot of times if you have a moving part, there'll be a force applied, or if you have pressure in the system, that pressure will exert a force across the surface area which needs to be, I guess, withstanded by the material or the metal. So we can use something called a tensile testing machine to relate stress and strain. So stress is the force applied per unit area to a part or to a sample, and you can measure the strain, which is looking at the increase in the length. So if you say pulling on a sample, by looking at the increase in length, so as you stretch it out, the change in length divided by the original length, that gives the strain. Here would be an example of a tensile testing machine. So we have a sample that's in between two plates that are being pulled apart. So as you pull them apart, you could actually measure the force that's being applied, the stress, and then you could also look at the distance that they're being pulled apart, which is related to the strain when you divide the change in length over the original length. Can then generate something called a stress strain diagram, and these are uniquely generated for every material, and they essentially show the type of deformation that can occur. And deformation just means losing its structural strength and how it will sort of deform, and then whether or not it will come back to its initial shape. So here's an example of a stress strain diagram. So on the y-axis you have tensile strength, which is measured, the stress, which is measured as the force per unit area. On the x-axis is strain, which is the fractional increase in length, or just the change in length over the original length. So as you can see, there are a few regions here. There's a straight line section, and this is what we call elastic deformation. And at this stage, as you apply a stress, there'll be sort of a uniform strain that develops across the material. And if you relax that stress, the material would actually go back to its original form. And that's why we call it elastic, because it's just like an elastic. When you pull it apart and let it go, it'll snap back to its original size. And that works for metals as well, as long as it's in this elastic deformation zone. Now, beyond a certain point, after a certain stress has been applied, the material will no longer be able to withstand those forces. And you get into a region called plastic deformation. And that's where the material is now deforming in a way that if you release the stress, it won't go back to the initial state. As you can see, the curve goes a little strange up here in the plastic deformation zone. And an example of that would be if you have an elastic and you pull it, and eventually you get to a point where the elastic will start stretching and it won't go back to the original size and shape that it was at the start. And then if you go even further and pull it farther and farther apart, you'll actually cause the material to fracture. And it's at that point when you sort of really reach that maximum that gives the tensile strength, the amount of force that the material can withstand before it completely fails. And that's something that's useful to know when it comes to designing systems, because you want to make sure that you're far away from that maximum yield strength when you're operating a piece of equipment. During the elastic deformation, that's that part that's the straight line section when you could actually have elastic deformation and it would snap back to its initial size. The slope of that graph is something we could define as the modulus of elasticity. It's just a useful property of different materials. It's essentially the slope, so the rise over the run, or the stress sigma divided by the strain epsilon, and that parameter is what we call the modulus of elasticity. Here, the stress is given in force per unit area, so that's a pressure unit. So an example of that would be PSI. The strain epsilon is a change in length over length, which just gives a dimensionless parameter. And so ultimately the modulus of elasticity has units of PSI. So this is one property that you'll learn about in the material science course, and it can be useful in selecting materials for various applications. So that's it for the materials lecture. Stay tuned for lecture 2, which is going to cover process controls and economics, and that's going to wrap up the lecture series in this class. So that'll be the end of section 5. I will see you again.